Ready, Marcel? Okay, let's go. Right, so here's our beta distribution, and now I'm going to show you why it's useful. I'm going to go with this formulation of the beta distribution with a constant of proportionality here. See, I'm saying is proportional to?
How can you tell the difference between that proportional thing to alpha?
Oh, that is a good point. The question was, it looks like an alpha. That is a very good point. Let me...
Right.
Yes, that is a very, very good point. This is proportional to. You can tell it's not an alpha because what alpha does for p, beta does for 1 minus p. So it's a sort of symmetrical relationship between alpha on the left and p. And if you just muck it up by putting another alpha there, it wouldn't be symmetrical.
Yeah, I understand that, but it's just the drawing.
It's not very nice, is it? It's a kind of a infinity symbol with a bit missing.
Okay.
But yes, that's a very good point, which I've not been very clear about. Okay, let's go back to Bayes' theorem now. The probability of your hypothesis given your data equals probability of your hypothesis, which is your prior, P of D given HI, over some stuff. And that stuff on the bottom doesn't really have any function other than to make your probabilities add up to 1. So I'm going to say that the probability of HI given D is proportional to the same symbol as that, and I'm not writing it very neatly, P of H, P of D given HI. And that constant of proportionality is, well, 1 over that stuff there. All right? So now I'm going to move notation. Instead of talking about HI, I will use P to mean the hypothesis that is the hypothesis that the probability of success equals P. So you might say P equals 0.5, and that says, I'm telling you, that's my hypothesis, that P equals 0.5. The probability of success equals 0.5. So I can say P equals 0.1, and I'm saying that's the hypothesis that the probability is 0.1. So here's this is kind of a cut down Bayes' theorem. So what does it tell us if I make this notational change? The probability, now this is, I'm riding slipshod over subtle mathematical details about continuous and discrete random variables, but you'll see it all makes sense. Let me write that out again. There's a lot going on here. And when I taught this course last year, I just wrote it down saying, look, that's Bayes' theorem, deal with it. But I'm going to spend some considerable time unpacking this because it's hard. In fact, I'm going to change colour. P equals probability of success. which is a free variable. I'm going to adjust p, and I'm going to show you what happens when I make p bigger and smaller. D equals my data equals 10 trials and 3 successes. Yeah? We've got a prior for the probability of success, and the whole point of the Bayesian paradigm is that you can update your priors in the light of data. So you've got a prior about what you think p is, and remember we talked about lots of examples with the uniform one and the bimodal ones and so forth. Now we're going to throw some data at it. Yes? Yes? And I'm not sure if I've used this word, but if I have, you will recognize it as likelihood. Have I said the word likelihood before in this course? Sometimes I introduce it really early on and sometimes later. And I don't think I've used it yet. Certainly not in its correct sense. Is that everything? Oh, no. Posterior. I think I've covered everything here. I think I've covered all my terms. So P and D, prob of P given D is the posterior. Prob of P is the prior distribution before you look at your data. And this thing here is a likelihood, probability of seeing your data given P. All right? And it's a constant of proportionality because we've got that gamma function business on the bottom, which I'll put in later. I'll come back to that.
Sorry, in this case, you have prob P over D.
This one.
Yeah, the very beginning there, yeah.
This is the posterior. We want this.
Yeah. So the P though, you have P inside the brackets is the probability of success, where the
Which one are you looking at? This one or this one? This one?
I'm seeing you have probability and then you have P.
Probability of P given D.
Okay.
So that's the posterior because this is the prior.
Okay.
And there, I'm saying, well, what do you think now you know the data? And here's the data.
Okay.
So we've got the prior, we've got some data, we've got a posterior. So we're going to update our beliefs in the light of data. That's all we're doing. All we're doing is putting a D after there, and that's what the formula is.
Okay, so your formula is you've got your probability, your prior probability,
Yep.
multiplied by your
Multiplied by the likelihood.
likelihood.
Divided by something, and I've represented that stuff with the gamma function as this constant here. Let me just show you. I appreciate your questions, but it will all snap into clarity when I show you how it works. The prior is going to be proportional to p to the alpha minus 1, 1 minus p to the beta minus 1. We've talked about that as a prior, and we've got lots of examples of it working. What is this? What is the probability of 3 out of 10? No, let me write it out differently. The probability of the data given p equals the probability of 3 successes out of 10 trials given p. All right? Well, that is just binomial, isn't it? Remember the binomial distribution? All right? You happy? Is anybody not happy with that? Because it's binomial distribution. So now we're in a position, we know that because I've written it down. We know that because that's binomial. Now I can just multiply one by the other and get the posterior. Isn't that clever? That's just Bayes' theorem again, constant of proportionality. All I'm doing there is just writing in my terms. Isn't that clever? And now I'm going to observe 10 choose 3 is just a constant. Because there's no p in it. And because I'm only considering proportionality, I'm just going to drop that. So the posterior is proportional to p to the alpha minus 1, 1 minus p to beta minus 1, p cubed, 1 minus p 7. Yeah, I've just dropped the constant. Which is proportional to p to the alpha plus 3 minus 1, 1 minus p to the beta plus 7 minus 1. Which is a beta distribution. So to summarize all that process, we start with the beta distribution. We apply Bayes' theorem to sharpen it up in the light of data. And as if by magic, we have another beta distribution, which is your prior, which has got different parameters, for sure. Instead of alpha and beta, it's now alpha plus 3 and beta plus 7. And there's nothing special about 3 and 7 here. I just made those values up for it to be concrete. I just wanted to have a smaller number of abstractions when I was talking. So this example, this uses okay, but the same logic so if you've got that, you can again observe that your posterior is proportional to p to the alpha minus 1, 1 minus p to the beta minus 1, which is your prior. Likelihood. For the general case, here I've got 3 and 7 as examples. Here I've got A and B. I just wanted to give a more concrete example, but I'm not sure if that was very helpful in this context. And rewriting. It's a little piece of mathematical magic, that. It's called a conjugate prior, and I'll talk more about that later on. Usually when you do Bayes' theorem, it ends up as a total mathematical dog's breakfast. But in this case, we've got this beautiful paradigm. We've got the prior, we've got the data, and the posterior. A successes and B failures. The posterior is a beta with alpha plus A and beta plus B. It's turned a beta distribution into another beta distribution with different parameters. It's like, and we'll see examples of this in the course, it's like you've got a Gaussian distribution, you throw some data at it and you change your mean or you change your standard deviation. It's not Gaussian, but it's like it. All right, example. Your prior has got alpha equals 1.6, beta equals 3.5. Your data has got A equals 10 and B equals 14. That's successes and failures out of 24 trials. Then your posterior will be a beta distribution of 1.6 plus 10, 3.5 plus 14. You just add the parameters together. We'll see generalizations of this later on. So let's have a look at that. Let's have a look at that in R. I've still got my P, a sequence from 0 to equals 1, length equals 100. What was it? 1.6, 3.5. 1.6, 3.5. There's my prior. So he thinks the probability is probably somewhere around here, probably 0.2, probably not 10 to the minus 15, and it's probably not 0.999999 because the curve's too low there. Probably somewhere in between, but on balance, probably sort of slightly on this side of 0.5, but not. You see the way I'm talking? I'm kind of using vague, intuitive, subjective, feeling type words. Subjective prior, which is a controversial and emotive, difficult topic for statisticians to talk about, certainly me. And I spend a lot of my time dealing with the difficulties of this kind of subjective language when I'm dealing with matters such as the future of civilization, because I'm working in the Bayesian paradigm for climate change. And it's not clear to me what the correct statistical approach is in climate change. And this is important. This is the future of civilization. And we are arguing about the shape of curves. It's a very peculiar, surreal situation. Okay, well that's my posterior. Just set up a new window here. And then I'll just add my observations. What was my observations? 10 and 14. 10, 14. So there's my prior, and there's my posterior. Put one on top of the, oh actually I can put one on top of the other like this. Here we go. Prior, posterior. Sharpened it up. Why is it sharpened up? Because we've thrown some data at it. What does data do? It reduces your uncertainty. What does data do in terms of your limits of where you think it's going to be? It brings them in. It's nice, isn't it? Isn't that clever? Don't you think that's really, really clever? from an educational perspective, I'm pleased that I can do this, and I've had to skirt around the issue, but it's rigorous nevertheless. I've had to skirt around the issue, but I can do this without calculus. I can still show you how these distributions work without invoking differentiation or integration. I'm quite pleased that you can do that. It's not clear, or it wasn't clear when I started teaching this course that you could do that. Let's throw some more data at it. Stacks of data. What's going to happen? Even narrower. Isn't that great? We started out with our prior distribution, which is quite wide. Notice how it shifted it over to 0.4, because now we've got so much data, it's swamping your prior. You've almost, not quite, but almost forgotten about your prior beliefs because your data has squashed them dead. That 40 is dominating this crap 1.6. That 54 is walking all over this 3.5. You can see that the sizes of your data is so strong compared to your priors that it's walked all over it and extinguished it almost, which is a nice feature. That's how you should update your beliefs. What you should do is your data comes in, you're updating your beliefs, and eventually your data is so strong and so informative and so powerful, your data has just, your original beliefs have just fallen off the bottom of your list. Does it actually work like that? Of course not. In practice, people come up with 1,001 reasons to ignore this data. In practice, people say, well, you collected it and you're terrible, so I'm going to ignore that. In practice, people say, well, I'm just going to ignore that data because it disagrees with my opinions. This is an idealization of the scientific method, which does not apply in practice. It should do, but it...
Because you're involving basically faith.
Yes, basically.
Faith and belief to not.
People's faith and belief are very, very difficult to shake by not so much rational arguments, but by presenting contrary evidence. There's all sorts of psychological mechanisms that people use to maintain their beliefs in the face of contradictory data. This is how you should do it, but it's not how it works in practice. What time is it? It is 10:30. I'm going to concentrate on one specific feature of Bayes' theorem. I'm going to ask, oh, for goodness sake, I'm going to concentrate now on, I'm going to ask what happens if I, the statistician, ask for a prior This is an extraordinarily frequent occurrence. This is a relatively simple case, but it's not that different from the real cases I deal with in climate change. Quite often I will say to my expert, who is in a position to give me data and who's in a position to know about these things, I will say, what is the prior? And he says, I just don't know. And I say, well, the prior, let's just concentrate on this. The prior is a representation of what you think. And he says, well, it could be anything. And I say, well, give me a prior. And he says, basically, he says no. And I say, well, can I use a uniform prior? And he says, this is an extraordinarily common problem. It's called elicitation. In fact, I'll write it down. Elicitation of a prior. And I'm only half joking when I say that the only way to get a prior out of some people is to lock them in a room and don't let them out until they give you one. And I literally have to do that sometimes. I say, I need a prior. You're wanting me to give a posterior PDF, aren't you? So you have to give me a prior. And I can't get one out of him. And I say, you're not going home. You're not even going to the bathroom until you give me a prior. And the Bayesian paradigm, which takes this posterior and prior business very seriously, says, well, this is a problem, but we have to do it. I think it shows a fundamental flaw in the mathematics of the situation. But I have a minority viewpoint on this. Problematic.